Next, I would like to introduce Jeffrey Chung, who is providing us the IETF BESS WG update. Jeffrey is a distinguished engineer with Juniper Networks routing protocols team. He has worked on routing technologies for over 30 years, from OSPF, BGP, LDP, RSVP, MPLS TE, MPLS BGP based services to multicast PIM and MVPN, VPLS, EVPN, and Rift, segment routing, and mobile user plane. Jeffrey is an active IETF participant, and he co-chairs the RAFT and BESS WGs, aka working groups, in the IETF, while also participating on the NANOG program committee. Welcome to the stage, Jeffrey.
Thank you. Thanks. Good afternoon. So I'm going to give an update on the IETF BESS working group. BESS stands for BGP Enabled Services. This is on behalf of the BESS working group chairs. So I'm going to give a quick overview of the working group, and then we'll talk about the past work that BESS working group have done, and some ongoing work, and end with the summary. So BESS, BGP Enabled Services. That link there has the information about that working group. It's one of the most active working groups in IETF. We define, specify, or extend network services based on the BGP protocol. Specifically, BGP signals, IPVPN, and Layer 2 VPN. We work on the protocol mechanisms, OAM mechanisms, and data models. We work closely with other working groups like IDR, which defines the BGP standards, and the Spring working group, and so many other working groups. So we have 3 chairs: Matthew from Nokia, Stefan from Cisco, and me from Juniper. We have a secretary, Mankmana from Cisco. Our area director is Gunter from Nokia. The participants of these working groups are individuals from vendors, operators, and academia. It was previously the L3 VPN working group. It was in the 2014 that it was extended to include all services enabled by the BGP protocol. Nowadays, we mainly work on EVPN-related technologies. It just so happens. Some past work we talk about here actually were done, were finished in the L3 VPN working group. So let's talk about the past work that the BESS working group has done. Virtual private LAN services. In other words, emulated LAN services. So when we spell out as virtual private LAN services, we refer to this general emulated LAN service. And then if we say VPLS, the abbreviated form, then we refer to a specific solution that provides virtual private LAN services. Long time ago, we used VPLS, and then we have evolved to EVPN or Ethernet VPN. So VPLS uses LDP or BGP signaling to establish that services among the PEs. And so you can think of this virtual private LAN services. You can think of the provider network as a huge switch or bridge, and you have your edge PE devices connected into customer equipment CEs, and then you learn the MAC addresses on your PE CE link, But in the case of VPLS, among the PEs, you also learn the MAC on the provider tunnel that gets the customer traffic from PE to PE. With the EVPN, we just use BGP signaling, and we do not do MAC learning between the PEs. The MAC addresses are advertised among the PEs, just like in the IPVPN case. A very important feature of EVPN that is the all-active multi-homing, which we will talk about in the following slides. And of course, there are a whole bunch of other features, so we will talk about some of those. RFC 7432 is the base spec for EVPN based on the MPLS data plan. So it has been widely used to provide virtual private line services over WAN, replacing VPLS, or can be used for DC overlay services, collecting servers. It can be used for data center interconnect, provider backbone bridging, and even pure IP overlay services. Even if you're not doing layer 2, if you're just doing layer 3 VPN, you can also use EVPN, and we will talk about that. It can be used for both unicast and multicast. In fact, we have some interesting deployments where providers would use EVPN to provide IPTV services. A lot of multicast use there. So, EVPN all-active multi-homing. I'll first talk about how the unicast works. If you look at the picture on the right side, we have a CE2 at the bottom using lag connect to PE2 and PE3. So from PE2 and PE3's point of view, they connect a multi-homed Ethernet segment. And then at the top, we have PE1. So let's say PE1 receive traffic from CE1, and it needs to reach CE2. And PE2 has previously learned the MAC address of CE2. So PE2 advertise to other PEs in BGP, hey, I have this MAC route. Now PE1 knows that PE2 advertised the address. It also knows that both PE2 and PE3 are connected to the Ethernet segment. So PE1 has a choice to use either PE2 or PE3 to send traffic, even though PE3 did not advertise that MAC route. So that's the aliasing feature of all-active multi-homing. Here so if you are familiar with EVPN protocol, you know we have all kinds of types of EVPN routes. Here, I will not get into that kind of details. Now, another feature is mass withdrawal. Imagine that PE2 and PE3 has learned a lot of MAC addresses and advertised into the network. Now, the PE2's link to that multi-home segment goes down, then a single route withdrawal from PE2 will cause PE1 to reroute away from PE2. That's mass withdrawal. Another important aspect with multi-homing is bound traffic handling, broadcast, unicast, unknown unicast, or multicast traffic. That involves a concept of designated forwarder. In this case, PE3 is the designated forwarder for that multi-home Ethernet segment. If you look at the blue traffic from CE1, bound traffic, it will be sent by PE1 to both PE2 and PE3. Now, only one of them, PE2 and PE3, will send the traffic to CE2, and that's the role of the designated forwarder. Another important aspect of this is the split horizon. Look at that red bound traffic from CE2. It reaches PE2, and then it gets sent to PE1 and PE3. Now, PE3 must not send the traffic back to CE2. So that's called split horizon. And there are two ways to do split horizon. One is what we call ESI label method. So when the PE2 receives the bound traffic from CE2 and send it to PE1, PE3, it carries a label that identifies the source of the Ethernet segment. So then when PE3 gets that traffic, you notice that, oh, this traffic came from that multi-home segment that I am on. So in that case, I will not send it back to that Ethernet segment, even though I am the designated forwarder. The other method is the local bias. Now, this time we look at the green traffic from CE3. When PE2 receives that traffic, it will send it to CE2, even though it is not the DF for that Ethernet segment, because it's doing the local bias. Now, when the traffic arrives on PE3, PE3 knows that, oh, this traffic is from PE2. I don't know which segment it came from, but I know it's from PE2. And I know that I have a multi-home Ethernet segment that PE2 is also on. In that case, PE3 will not send it back to that segment either. So that's the local biased. The ESI label method is used for MPLS network, and local bias method is used for IP data plane. So we talk about the basic, the important EVPN features, especially the multi-homing. Now, there are different EVPN variations. RFC 8365 is EVPN with VXLAN and NVGRE data planes. For comparison, RFC 7432 is EVPN with MPLS data plane. And we also have E-tree and E-line. So when we talk about virtual private LAN services, it's a LAN, so it's any-to-any service. But when we talk about E-tree, then we have some nodes are routes and some nodes are leaves. In the case of E-tree, we only allow the traffic between the routes and leaves. We do not allow leaf-to-leaf traffic. And E-line is a point-to-point service. We're just using EVPN to provide the point-to-point virtual private wire service. There are many EVPN extensions. DF election extensions are very important. There is this RFC talk about extensibility framework for DF elections. There are all kinds of optimizations, enhancements for DF election. There is time synchronized DF election. It's in the RFC editor's queue. It's being approved as a standard. It just has not been published as the RFC yet. And there, I'm going to skip the 4 other RFCs on this slide. I want to talk about some other ones. Here, there is RFC about interconnecting EVPN and data centers with RI specifying the procedures for integrating with EVPN and the VPLS. Even though EVPN is becoming a mainstream solution, there are still a lot of VPLS deployment. And sometimes you want to get a two solution to play together. The next two RFCs are 9135, 9136. I'm going to talk about in the next few slides. Inter-subnet IP unicast forwarding. So when we talk about EVPN or basic virtual LAN services, right? So it's a layer 2 concept. Each broadcast domain corresponds to a IP subnet. Now, in this case, I have 2 PEs. PE1 has 2 broadcast domains BD1, BD2, and PE2 has BD2 and PD3. And we have TS1 through TS4 there. TS stands for tenant systems. Now the traffic from TS1 needs to reach TS2 on different broadcast domain or different subnets, and so reach the TS3 and TS4. How does it work? This is via integrated routing and bridging. Here it involves IPVRF for inter-subnet routing, and also bridge tables for inter-subnet switching. There are two modes to do this. First one is symmetric. If you look at the traffic from TS1, it reaches the PE1, the big box on the left side. It goes into that bridge table 1 for broadcast domain 1. It does a MAC lookup. It matches a local system MAC address. It knows that, oh, this is packet, this frame is for me. Then it sends up into layer 3 in the IPVRF. We do a lookup. We find out, oh, this needs to go to another PE2 on the right side. When the traffic arrives on the right side PE2, it lands into the IPVRF and do an IP lookup, find out it needs to be sent into broadcast domain 2. So the traffic is sent into a bridge table 2 for lookup and eventually goes out. So there are two IP and MAC lookups on both PEs, symmetric. In this case, we need to maintain bridge tables and ARP entries for local tenant systems only. The next one is asymmetric mode. If you look at the lower right picture, after the first lookup in the IPVRF on PE1, it goes into the bridge table lookup on the same PE into BD2 and BD3, and then send over to the other PE at the layer 2. And there is no IP lookup on the second PE anymore. So this is why it's called asymmetric. This does require all the bridge tables and all the ARP entries needs to be maintained everywhere. So this is the only slide where I mentioned the type of routes here. People are used to call it, okay, type 5, EVPN type 5. So EVPN started with the MAC route, right? So we advertise a MAC route among the PEs so that you can forward traffic based on the MAC lookup. It can also advertise IP addresses associated with those MAC addresses, and then it's extended to advertise IP prefixes, also with the overlay index. The overlay index is treated as a BGP protocol next hop. You can do a recursive lookup on that overlay index. The difference between the overlay index and the regular BGP protocol next hop is that that overlay index is in the tenant's address space. It could be a Ethernet segment identifier, it could be a MAC or IP address in the tenant's address space. This allows mass updates of IP prefixes. You could have thousands and thousands of IP prefixes tied to the same overlay index, and if your overlay index route changes, then with that single updates of the overlay index, you can update a lot of routes. Besides that use of the overlay index, you can use the single address family and supplementary address family pair that is used for EVPN to provide both layer 2 and layer 3 VPN services. You don't need IPVPN and FE anymore. Even if you're not doing L2 at all, you're just doing L3, you can also use this. And the use case for that came up because some operators wanted to do VXLAN data plane for IPVPN. And at that time, this was a perfect solution for that. You just because EVPN you can use VXLAN data plan, and you can use it to provide layer 3 VPN services. So some more information on the bomb handling in EVPN. If you look at the picture here on the right side, we have 4 PEs, and then PE2 and PE4 receive the IGP join for S, G pair. Then they will turn that into BGP routes, what we call the selective multicast Ethernet tag routes. Basically, it's just translation of the IGMP signaling. When PE1 gets it, it translates back into the IGMP signaling into towards the CE. So that's the proxy between the IGMP messaging state and the SMET state. Going along with that, you can do the selective forwarding. Notice that here, P3 did not send that, did not receive that join, and did not send the SMET route. Therefore, when P1 gets the corresponding multicast traffic, it does not have to send it to P3. That's selective forwarding with ingress replication. By the way, the base spec covers bomb forwarding, but it assumes inclusive forwarding. Does not do selective forwarding. It basically, you send it to everywhere, every PE. Another updates on the bomb is this RFC 9572 is it's more advanced topic for the bomb handling. It covers selective forwarding with point-to-multipoint tunnels. It handles covers inter-AS, inter-region segmentation, where in different ASs or different areas, you can use different provider tunnels for multicast traffic. Assisted replication is yet another bomb feature that is used widely. Look at this picture on the upper right corner. You have PE1 through PE4. Now, let's say that PE1 needs to send multicast traffic to all other PEs. If you do ingress replication, P1 need to send 4 copies, 3 copies. It may not be that bad, but if you have 100 PEs, sending that 100 copies, it may be too much a burden for individual PEs or leaf switches in the data center. So you could have an assisting replicator. Then each PE will just send it to the replicator, and the replicator will then relay the traffic to other leaves. That's the assisting replication. Inter-subnet multicast. In this picture, we have PE1 and PE2 with broadcast domain BD1 through BD3. We have a resource on BD1, receiver on BD2 and BD3 on both PE1 and PE2. Now, remember that each broadcast domain corresponds to an IP subnet. So when you need to get multicast traffic from one subnet to another subnet, you can just use the plain old pin-based multicast forwarding. So you can just have that multicast router connected to PE2, and then you can treat each broadcast domain as an emulated LAN here. So when traffic from the source reaches PE1, then it gets to send to the multicast router through the broadcast domain 1. And then the multicast router does the forwarding, inter-subnet forwarding, and routing that traffic into subnet 2 and 3. Now, there are 2 problems with that model. First one is the traffic hairpin. Notice the traffic from source to receiver 1. Even though both source and receivers are on the same PE, you still have to get the traffic to the other PE, to the multicast router first, and then come back, hairpin. Another problem here is that, notice that traffic goes across the core to the multicast router, and come back with 2 copies, one through the broadcast domain 2, the other one through broadcast domain 3. So optimized inter-subnet multicast, or OISM, removes those 2 drawbacks. Basically, in the source broadcast domain, we switch the traffic to both local and remote receivers in the same source broadcast domain. It's inter-subnet switching. The source MAC address does not change, and TTL does not change. And then each PE will route multicast traffic across subnets to their local receivers. If we look at this picture again, when the P1 receives the traffic from the source, it will locally route to BD2 and BD3, and they also switch to PE2 for the receiver 3 in the same broadcast domain 1. So this optimized inter-subnet multicast is covered by RFC 9625. The concept is actually very simple, but the spec is quite long because it covers some, it explains, it took quite some effort to explain the IRB concept. It talks about different provider tunnels, whether it's P2MP or ingress replication. It covers situations where you have some P support the OISM procedure, some other Ps who do not. And it covers a lot of other situations, so the spec is long, but the concept is actually quite simple. So now, past work on MVPN, or multicast IPVPN. So when we talk about VPN, you can think of the provider network as an emulated LAN, with the PEs being the multicast routers with upstream senders and downstream receivers. Then in this model, you have 2 problems to solve. How do the downstream PEs signal their customer multicast interests to upstream PEs? The other one is that how does an upstream PE send customer multicast traffic to downstream PEs through the core network? Actually, the same 2 problems apply to EVPN as well. We talked about those for EVPN briefly without calling them out explicitly there. So this RFC 6513 is basically a framework to cover both BGP and PIM MVPN. So in case of PIM MVPN, we use PIM protocol to signal the customer multicast states among the PEs. You basically run the PIM protocol over a pseudo interface that is instantiated with a PIM multicast tunnel. And in the case of BGP MVPN, we use BGP to signal the multicast, customer multicast state. And in both cases, you can use BGP to signal the traffic to provider tunnel binding, whether you want to send traffic to all the PEs, or you just want to use the selective tunnel to send traffic to some PEs that need the traffic. And then we have RFC 6514 specifically for BGP procedures and encoding. And then there is also a RFC that covers global table multicast using BGP MVPN procedures. Yes, you are doing multicast in the default instance, but you can still use the VPN procedure. So here we have a list of RFCs for various features related to MVPN. The first one, hot warm root standby for multi-home sources. Imagine that you have a deployment that you use MVPN to send IPTV traffic, and you may want to make sure that if something happens in the network, you can have A-B feed, and then they both reach the egress PE, and the egress PE will choose which feed to forward to downstream. So that's the hot standby. Warm standby is that you prepare the upstream PEs enough so that they can quickly switch over to start sending traffic if the other feed stops. I'm going to skip most of the RIs RFCs on this slide. The last one, inter-area segmentation, I'm going to illustrate it using this diagram here. Let's say that you have this nicely formed 5 areas, area 0 in the middle, and then you have other areas surrounding it. And those small rectangles are the PEs. Now, to get the customer multicast traffic across this network, you can use, we use provider tunnels, which could be ingress replication provider tunnel, it could be RCVP, P2MP tunnel, MLD, P2MP tunnel, or you can use BEER. A lot of different technologies. So this end-to-end P2P tunnel, they can have different segments of different types, or if it's the same type, you can have different instances in those different areas. For example, in the area 1, you can use ingress replication. In area 2, use RCVP, P2MP tunnel. And in the area 0, you can just use BEER and so on and so forth. That can be for technical reasons, or it can be for the admin reasons. One thing here is that the RFC is based on the area boundary, but it does not have to be like that. And depending on the vendor's implementation or your deployment choice, you can do this even you have a single flat IGP area. You can still do this segmentation. The benefit of this segmentation is that you can get around those limitations. For example, you have an area that you can only do ingress replication. You have another area or another ES you can only do LDP, MLDP, and so on and so forth. And then in case of ingress replication, you can reduce the fan out. For example, in this picture, if you have to use ingress replication without a segmentation, then the single PE in area 1 will have to do the individual copies to every other piece in the network. But with segmentation, you only need to ingress replicate traffic to the PEs in your local area plus that area border router. And then at the area border router will further do the ingress replication. So other past work. The first one, 9252, is about overlay services using SRv6 data plane. In the past, a lot of services are based on MPLS data plane, and now SRv6 is becoming more and more popular, important. And how do we do the overlay services, whether it's IPVPN or EVPN? How do we do it using SRv6 data plane? And at the bottom of this slide, DCB common label, which I will explain in the next slide. So let's say you're doing multicast VPN or you're doing EVPN that supports bomb traffic. We talked about you have to use provider tunnels to send the traffic across the provider network. You can use a P2MP tunnel or you can use ingress replication. If you're using P2MP tunnel, typically you use one P2MP tunnel for every VPN or for every broadcast domain. But sometimes you may want to use a single P2MP tunnel for multiple VPNs or multiple broadcast domains. In that case, you will need one label stacked on top of your provider or your P2MP tunnel to indicate which VPN or which broadcast domain it is for. That label used to be upstream assigned, basically the ingress PE will use a label for VPN1, another label for VPN2. That label is assigned from the ingress PE's label space. Because of that, every PE need to maintain a label forwarding table for every ingress PE. And that has a huge scaling problem. For example, if your network has 1,000 PEs and each PE needs to support 1,000 VPNs, then you will need to use 1 million labels for all the combinations. That is not going to scale. So this DCB label is to address that problem, as DCB stands for Domain-Wide Common Block. It's the same concept as the common sRGB, Segment Routing Global Block. It's just that here, this concept is independent of SR, so we use a different name. It's basically a global label. All the P's agree that label 100 is for VPN1, label 101 is for VPN2, and so on and so forth. With that, the implementation is easier, or the operation is easier, and scales much better. Okay, moving on to ongoing work in the BESS working group. We talked about the EVPN multi-homing split horizon earlier. You can use ESI label or approach, or you can use a local bias approach. There are some data planes that you can actually do either. You either use ESI or either use a local bias. This draft talks about how you are going to do that, how you make that choice, how to signal that. And the EVPN redundant multicast source is basically the equivalent of that hard root standby that we talked about earlier in the layer 3 VPN, but this is for the EVPN. The base spec for EVPN has been out for quite some time. We've gained a lot of deployment experiences. We found some issues. So we are working on a revision on that base spec. So that's what we call RFC 7433 BESS. That is ongoing work. EVPN BFD use the BFD to do the proactive in-band network layer OEM. EVPN Geneva, yet another data plane for EVPN. EVPN MEPN seamless interop. Earlier we talked about OISN, optimized inter-subnet multicast, where we do layer 2 switching in the source broadcast domain. We do the routing and locally on each PE across subnets. Another way to support inter-subnet multicast is defined in this draft. It basically uses the BGP and EVPN procedure for that purposes, but it has one characteristic that may be a problem in some deployments. In some most deployments, it's probably not the issue, but the source MAC address and TTL change. Even you are sending the traffic in the source broadcast domain. It should have been done in the using pure layer 2, but this is always layer 3 routing. But it's an alternative when that is not a concern. EVPN and DPass is equivalent of BGP AS pass. You can have many EVPN domains interconnected, and how do you prevent looping from that? And so this concept of a domain pass equivalent to AS pass. And you have EVPN inter-subnets, IPVPN, and even just global IP interworking. That's it's specified in that draft. Yeah, IPVPN interworking. and two other drafts about designated folder selection. And IP aliasing, we talk about how P1 can send traffic to P2 and P3 that are on the multi-homing segment, that as the MAC level. That same concept can be extended to the IP level. So that's the IP aliasing draft. And then I'm going to skip that last one. We EVPN support MAC mobility. A CE device can move from one P to another P, and sometimes that mobility can result in the new IP and MAC association, so that draft covers that situation. Unequal load balancing. When you have multi-homing situation, another remote ingress PE can send traffic to either of that PEs on the multi-homing segment. Depending on the bandwidth available on the attachment circuit of PE to that multi-homing segment, you can load balance the traffic according to the bandwidth on the attachment circuit. Ongoing BESS work on multicast side, at layer 3 level. There are two drafts about using BGP to do the multicast signaling. The first one is about hop-by-hop multicast tree signaling and source discovery. It uses hard state signaling instead of PIMS, soft state signaling. And also use BGP to distribute source information, so you do not have the complexity of the PIM ASM mode where you use RPT tree, share tree to send traffic and then switch over. A lot of complexity comes from the PIM's ASM support. By getting rid of that, then the multicast protocol is simplified significantly. The controller draft is about using the BGP to signal tree setup from the controller to individual tree nodes. And then we also, that last draft is about using SRP to B tunnel to do, for MVPN or for EVPN bomb traffic. Other works, ongoing works, the first draft, V4, V6P, all SAFE, that draft talks about using a single IPv4 or IPv6 single stack for all FE SAFE that you may have on a PE. I think I can skip the other drafts on that slide. Some drafts, I'm not quite familiar with the exact work there, but I listed there just to show that the work ongoing. And if you are looking at the slides, you can follow the link and find out what it's about. There are also lots of other individual drafts. Some of them will be adopted by the working group. By the way, in IETF, the contributors will introduce an idea, a proposal in the form of individual draft. Then going through some working group discussions, and the working group decides that, okay, we are going to take up this work, we are going to work on this proposal, we are going to standardize it, and eventually it becomes RFC. That's the basic IETF process we follow. Summary, BESS working group work on many important services enabled by BGP protocol. Could be EVPN, IPVPN, or others. You can use MPLS data plane, IP, or SRv6 data plane, and so on and so forth. You have noticed that we talk about a lot of RFCs and drafts. A lot of them originate from the operator's interest because they have a specific problem to solve. And so the vendors and operators together, they come together and define a solution, standardize it, and they get deployed. Some of them were foreseen by some parties, they decide, okay, this is a problem worth solving, and this is the idea how we can solve it. So they work on that solution, and they standardize it. So you can see that during this process, the operator input and contributions are critical to make sure that we develop the best solution for the real problems. So that is why I'm giving this talk here, to talk about the work we do in BESS, and so to get your input and also to provide the update to our operator community, say that these are the features we have developed. Maybe some of them will be applicable to your network. So this is the end of my presentation. Thank you.
Thank you, Jeffrey. Is there any questions from the audience? Looks like we got one stepping up here.
Excellent, Prezzo. Thanks for the summary.
Thanks.
Anton Capella, 5 Could you touch on more directly the DF election process? Specifically, I'm curious if you could anticipate any complications for those of us who assume that bidirectional PIM just works. So along those lines, the procedures laid out, everything looks like it makes perfect sense until I ask, oh shoot, what might happen if I assume, say, redundancy in that process or high availability in that process in the context of the assumption of bidirectionality for all the distribution trees? Is there anything that you could anticipate or share with us about what you might think like along those lines?
So when it comes to DF election, there are a lot of extensions and optimizations, but there is one, I think it's one fix that addresses a problem that caused by the delay in the propagation of those messages used for DF election. And that's what I mentioned, there is a RFC2B. I call it time synchronized DF election. The actual draft is actually, I forgot, it's called something like DF fast recovery or something. But to me, the best way to say it is basically time synchronized DF election. When you have a whole bunch of PEs, you could have PEs come and go, and then whenever a new PE appears, they exchange messages to elect a new DF, right? So if you have considered the propagation delay of those messages, then you could run into a situation where momentarily they don't have the synchronized, they don't have the consistent view on who is the DF. But with the time synchronized DF election, that problem is very well solved, because nowadays you can make sure all your devices on the network, they have very well synchronized clocks, and with that, the DF election becomes very reliable. So that is that RFC2B with time synchronized DF election. I think that's the most important one, and when it comes to the DF election.
Got it. Thank you.
Excellent. Alex, anything from the online community? All right. Okay, great. That would be a no. Once again, thank you, Jeffrey. We appreciate that.